Hi, so hopefully you got a few minute break and you could think about this a little bit. And we're going to go and do these two examples. Now this is methane. And essentially this has one carbon, if I can get this, and 4 hydrogens. And so essentially this guy right here, since it has different atoms, it has a carbon, 1 carbon atom, and 4 hydrogen atoms. This is what we consider a compound. Right? Now, just because it has atoms bond together, it also makes it a molecule. Now, hydrogen gas, it's just the same kind of atoms. So it is not a compound, but it is a molecule. Now, our body is composed of a lot of different atoms, but the overwhelming majority of them are, of course, oxygen is 65%. The next most abundant is carbon, it's 18.5%. Then you have hydrogens and nitrogens. So more than 96% of the body are these 4 atoms. 4% are included in these, which essentially are a lot of the electrolytes that you find in your body. You have calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium make up about 4%. And then you have trace elements. And this is incorporated in less than 0.01%. Now, trace elements, though they're a very, very small part of what you see, they are extremely important. Deficiencies in these things can lead to disease states. For instance, iron deficiencies. Iron is important for allowing the body to carry oxygen. So this can lead to anemia, which can cause tiredness, dizziness, and shortness of breath. Magnesium deficiencies can cause things such as osteoporosis and chronic fatigue syndrome, and it can allow you to get sick frequently. Copper deficiencies, again, can reduce white blood cell count and specifically neutrophils, and it can cause anemia. And zinc deficiencies can also cause things like growth retardation or a loss of appetite or impaired immune dysfunctions or impaired immune function. So trace elements, I always like to point this out, though they only constitute a small part of the composition of the body, they're very much needed for proper function. Now that we've kind of talked where you can find these different elements, let's actually start tearing apart atoms. Now this is an atom right here, and this is just a cartoon representation of it. And the center of it is called a nucleus. And the nucleus essentially is composed of neutrons and protons. Now if you look, these particular subatomic particles actually have charges to them. Protons are positively charged and neutrons are neutral. Now these guys weigh roughly what's known as 1 atomic mass unit. So when we're talking about how much an atom weighs, the mass is just going to be calculated using protons and neutrons. Outside of the nucleus is where electrons reside. Now these guys have a negative charge to them. Now I like to think of electrons, there's what's known as the Bohr concept of the model, which is absolutely wrong, and it basically says that electrons are outside the nucleus running around, almost like if you're thinking about a high school football field, how the track is laid around the football field itself and people run around it. That's the Bohr concept of the atom, and it's completely wrong. The idea is that electrons are essentially these clouds of negative charge. So essentially, it's the idea of when you're thinking about cotton candy, when someone looks at a big vat of cotton candy and someone asks them where the sugar is, the sugar is everywhere. It's right there. That's what makes the cotton candy. So I kind of like to think about that in terms of electrons. Where the electrons are, they are areas that you essentially, areas that are filled with this negative charge. And that's what electrons essentially are. Now, electrons are really, really tiny. They only weigh 1/1800 atomic mass units, which means it takes 1,800 of these guys to equal one neutron or one proton. And there is not a single element on the periodic table that even comes close to this. So anytime when we're talking about how much a particular atom weighs, what we're actually looking at is just the weight of neutrons and protons, because electrons are so small. I like to kind of think about it this way. If you are really wanting to know how much you weigh and you're really trying to lose weight, the idea is if you stand on a scale and you blow out the air in your lungs, is it going to make you weigh any less that you can actually detect? It's not. And that is the best example I can give is why they don't end up counting electron weight and the weight of an atom, because it's so small and minuscule, it won't make much of a difference. So just to let you know, this is a non-majors course, so that's about the level of depth that I'm going to stop with. Essentially, atoms are really, really cool because you have, electrons and are considered, this can get more complicated. You can go into what is actually composed of things like protons, and those are quarks. And then you can talk about leptons, which are essentially, you fit in particles like electrons. And I just wanted to point this kind of out to you guys a little bit to let you know that it does get more detailed than protons, neutrons, and electrons. But this is about where we stop because we don't need to know the detail of everything else. But if you take a chemistry class, they will get into these things because they're just really cool, because you start talking about why they have the charge that they have, and it has to do with different spins of the subatomic particles, and it's just a really, really cool topic. But, I just won't put you out of your misery today. Anyway, so this is the periodic table again. And so we're taking that periodic table and we're blowing one thing up. And this is carbon. And carbon obviously is really, really, really important when it comes to terms of biology. And so if you look here, you have the chemical symbol here, which is C, and that's a shorthand way of representing carbon, right? Now, you won't always, this gives you the name of the element, but there's a lot of time for which you get periodic tables. They're not going to give you that because they're either condensed or trying to give you a lot of information. So, especially when you get used to knowing these things, you start memorizing some of those. But anytime in exam 1, I will provide you a periodic table that has all the names and the shorthand symbols, so you won't have to memorize that. Honestly, you won't have to memorize any of this information. I think it's a pretty dumb thing when professors make you do that. The periodic table was devised so that there would be an easy way to be able to maneuver through elements and know what the weight and the atomic number was for those elements. It was never meant for people to memorize it. Now, if you look at the top here, where this number 6 is, that's what's called the atomic number. And that basically gives us the number of protons. So the protons actually tells us what element we have. So for instance, if I say you have 6 protons, no matter what, you always tell me that's carbon, because no other element has 6 protons. Just like if I say, well, you have 1 proton, what do you have? You would always say hydrogen, because the number of protons defines the element. Now at the bottom here is the atomic weight, and for carbon it's 12.011. Now the atomic weight or mass essentially is devised by taking all the different isotopes, which we're going to talk what an isotope is here in a minute, a carbon, averaging all their weights together, and that gives you this overall average. Because what the periodic table is it's giving you information on the average carbon that is present, and essentially it's the neutral or the neutral atom. It's not charged in any way. So the atomic weight, what you can divide here, if you remember what I said for a minute ago, these are the protons and the neutrons. So for instance on here, right, if I say how many protons do you have for carbon, you tell me 6. Then if I say, well, how many neutrons do you have? How do you think what I'm going to do is I'm going to pause it now, and I'm going to let you think about this, and then essentially that is where I'm going to start in the next video.